Hello and welcome to lesson 28, and we're looking at infinite sequence and series today. So we're kind of changing pace for a second. We're actually looking at limits of exponentials. It's really what we're looking at. So what's the goal today? I can apply the concept of infinite sequence and series in order to write rational numbers as fractions when presented to me in a decimal form. So it's kind of the end goal. So I'm going to lead us there step by step as we go through the lesson today. So a sequence is a set of numbers in a definite order. Now, if you recall from grade 11, the formula for a geometric sequence is t subscript n equals a r to the exponent n minus 1, where, and if you don't remember this or didn't get to this, it's not the end of the world. You just really need to know the formula. Tn is value of nth term. N is your term number. A is the first value in sequence. And R is your base. So there we go. So that's just, it will tell you in an example, if you're not sure what a geometric sequence is, an example when you multiply, let's say you start with 2 and you double every time, 2, 4, 6, 8, 10, that's not even close. That's going up by 2, that's a pretty good job, but that's not what I wanted. Sorry, multiplying by 2. Geometric means to multiply. 4, 8, 16, 32, 64, and so on and so forth. All right, so then you would have n equals 1, 2, 3, 4, 5, 6. So if I asked for T6, you'd be looking for 64. If I was asking for T4, you'd be looking for 16. All right, so that's the very quick review of geometric sequence or series here. So when we're analyzing the nth term, we're really investigating the value of the term as our term number approaches, and in this case we're looking at it approaching infinity. It's the first time I think I've brought that terminology in officially. So we're looking as it approaches infinity. So if I look at the limit as n approaches infinity for t of n, I'm really looking at the limit of n approaching infinity for the equation a r to the exponent n minus 1. Now if we go back to our properties of limits, a is a constant here, it's not going to change, so we're just going to put it out front. So we're really looking at the limit as n approaches infinity for r to the exponent n minus 1. Well, there's two cases here. For those that remember the geometric sequence or series, there's actually two outcomes that we need to analyze here. So over here, if r is greater than 1 is one of our scenarios, and our second scenario is if r is between 0 and 1, so if it's a fraction. So if you recall, if you did see this, this would be growth, so bacterial growth or financial annuity. This is decay or decrease, so you'd be looking at nuclear or radioactive decay, you'd be looking at depreciation of a vehicle, and so on and so forth. So when you write it in this sense, when we're analyzing it, for a, taking the limit as n approaches infinity, for r to the exponent n minus 1, we know that we're going to end up with a multiplied by, so as n gets really, really big, and r, for example, let's keep it simple, let's say it's a 2, and pick a big number, well, something bigger than 5, guys, come on. No, bigger than 100. Let's go to 1,000,000. I'll help you out here. So if I have 2 to the exponent 1,000,000, 2 to the exponent 1,000,000,000, what does it look like our value is approaching? And it's really not a value, it's a concept. It's approaching a number that we can't quantitatively define, so it's infinity. And when you multiply infinity by a number, you still get infinity. So if r is greater than 1, and we look at n going to infinity, the answer will be that the value will approach or be entering into infinity. Let's look at the converse case of that then. Let's look at the 0 to 1. So we have decrease or decline here. So n approaching infinity for r to the exponent n minus 1. So we still have a multiplied by. So what happens when r is a fraction? So a half. What happens when it goes to, the exponent goes to a million? 2 to the 1/2 to the 1 million, 1/2 to the 1 billion. So that's a half times a half times a half times a half, etc., etc. You get the idea. What's happening is you're ending up with a very, very, very small number. And when you get to infinity, which is not actually a number, it's a concept. When you get there, though, you're going to find that the value is 0, and a times 0 still 0. So those are your two properties for limits of exponential functions that you need to remember and be aware of. All right. So where's an application for this? I actually have an application prior to getting to dealing with fractions and numbers and so on and so forth. So my note, I guess, doesn't have all the little notation. Kind of a headache to do with the smartboard unless I'm writing. So here we go. So one of these applications, you've done this already. You just don't know it. So I'm going to see if you can make the connection while I go through the example. I want to determine the limit of the following. So what's the process when you are dealing with n approaching infinity? What you're really doing is you're trying to figure out which factor in this expression has the largest influence on the final value. And what you're going to find is adding to or squaring a number has a bigger impact. So if I had 100 squared versus 100 plus 2, squaring it has a much, much bigger impact. So in this case, the squaring has the greatest impact on the end result for this particular scenario. So it is a rational function. However, we are going to take out the largest impact and see what happens. So that means we're going to divide every term by n squared minus 2n over n squared divided by 4n squared over n squared minus 2 over n squared. When we do this, we're analyzing what that major factor, what it really does to the question. So in those cases, the n squareds cancel out. What about these other ones? Well, we end up with that n canceling the exponent and 2 over n squared. So when n gets really, really, really big, what's happening here? Well, the limit as n approaches infinity. Actually, I don't really need to write that line. Okay, let's just look at it. When n gets really big, what's happening to this? Well, there's only a 3 left, so nothing changes. So you're going to have a 3. What about this next term? When n gets really big, we have 2 divided by n. So 2 divided by a really big number is really 0, so it disappears. Down here, n squared divided by n squared, it cancels out. So what happens when n gets really big? Well, it's a 4. And here, 2 divided by a really big number squared gets to 0 a lot faster. So we end up finding out that the answer is 3/4. So as n goes to infinity, the biggest or largest value it's going to reach is 3/4. Over here, what's the largest factor that's going to influence this particular question? And it's going to be the cubic. The cubic has the greatest effect here. So what we need to do is we need to address that cubic by dividing everything by n cubed. So 3n over n cubed, 12n cubed over n cubed, plus 2n squared over n cubed. Doing a similar simplification, n cubes cancel, we get rid of that exponent. That one drops it to a 2, and that gets rid of that exponent. So what's happening? Well, we have 5 over n. So 5 over n, that would go to 0. And this one, 3 over n squared, that's just going to 0 faster. Here we would have a 12, so it doesn't matter what n is. And here we would have a 2 over n, and again, goes to 0. So in the end of this, both terms on top went to 0. On the bottom I have a 12. So it's really 0. Excuse me. And the final one. Okay. Oops. In that final one, we need to do the expansion. The only way this works is if it's expanded out in full. So we're looking at the limit as n approaches infinity for n squared plus 2n plus 1 over 2n. We're going to have to divide all our terms by n squared. So n squared over n squared, 2n over n squared, plus 1 over n squared, all divided by 2n over n squared. So, not sure where my thing went. There it is. So, when we reduce here, the n squareds would cancel, leaving a 1. This n, we get rid of the exponent. Nothing there. This n gets rid of the exponent. So what are we left with? We have the limit as n goes to infinity. On top, I will have just a 1. And the other two terms go to 0. And on the bottom, as n goes to infinity, it's going to make the denominator 0. We don't have any other recourse, don't have factoring or conjugate here, so therefore, no limit exists would be our answer. Now, my question over here is, when have we seen this before? Okay. So where did you see this or do something similar? And this goes back to your advanced functions course from last semester. Some of you are likely thinking or saying, we did this, we just never did it with limits. And you're absolutely right. The limit notation wasn't there, whether it was myself or one of the other teachers teaching it. We just tell you, do this process. All right, we tell you, just do this to figure it out. And what it is, this is the process to determine the location of horizontal asymptotes. So in this unit, I'm testing you on just finding the limits. Next unit, Unit 4, we got some graphing. You need to remember this because I'm going to ask you to find a horizontal asymptote. So that means you're going to have to take the limit as n goes to infinity. So you're going to be working with limits that go to infinity. All right, I'm going to finish the rest of this in the next video.